Welcome back. Let me remind you that we are in the middle of the discussion on pairwise sequence alignment. In the previous segment, we explained the most basic version of the algorithm. In this segment, we will describe three extensions that are very common in all computer packages that implement the algorithm. We will mention this extension briefly here and elaborate on them in the practice session. The algorithm we have discussed look for global alignment between two sequences. Namely, in the example we presented, we wish to align the entire sequence of the first molecule to the entire sequence of the second. However, in some cases, we know that the two molecules may be similar along only part of their sequence. In such cases, we may look for a local alignment, searching for segments of the sequences that can be best aligned to each other. This search may seem more complicated than our original one, since we need first to identify the segment that can be matched and only then align them. However, it turns out that simple modification of the dynamic programming approach, such as avoiding negative values and looking for the maximal value in the entire matrix, can find the optimal local alignment between two sequences. The second enhancement deals with setting a more realistic cost for each type of match and mutation, rather than the uniform cost we used so far. Amino acid, and to some extent even nucleotides, can't be classified in a binary manner as either identical or different from each other. For example, some amino acids are hydrophobic, so when we compare valine to leucine, while they are different amino acids, their substitution may not have much of an effect on the properties of a protein, as they are both hydrophobic. If we compare valine with arginine, they are much more different from each other, as valine is hydrophobic and arginine is positively charged. For example, if we see that a leucine and isoleucine tend to appear in the same position in homologous protein from different species, then we can conclude that these two amino acids can replace each other and thus are similar. If we see that in a position dominated by arginine, we hardly ever find a glutamic acid, then we can conclude that this pair of amino acids are not similar. The relative differences between amino acids have been quantified and are available in tables. There are two families of such tables, the PAM and the BLOSSOM tables. They differ in the way the relevant data were collected and the values calculated. These tables can be used together with the alignment matrices that we described previously to achieve a more meaningful comparison. I hope that now the distinction between sequence identity and sequence similarity becomes clearer. After alignment, we can count only the identical amino acid between the two sequences and report their level of identity, or we can count the number of similar amino acids above some threshold determined by the similarity matrices and report the sequence similarity level. The third extension deals with the processes leading to mutations. In the alignment we discussed, one gap of, say, 4 nucleotides has the same cost as 4 gaps of 1 nucleotide each. However, from experiment and from bioinformatic analysis, we know that this does not reflect molecular reality. The probability of a single genetic event that will lead to a loss of 4 nucleotides is much higher than the probability of 4 separate genetic events that will each lead to the loss of a single nucleotide. With some modifications, the algorithm can use what we call an affine gap penalty that assigns a separate cost for opening a gap and then additional cost for extending it. In this way, we can make the algorithm prefer alignment that include fewer genetic events. In the last two segments, we have discussed the basic pairwise alignment algorithm and its extensions. I apologize if it was a bit too technical, but it was important for me to show you the details behind one of the most important tools in bioinformatics. In the next segment, we will talk about more complicated tasks, such as multiple sequence alignment and constructing phylogenetic trees. So, see you next time.